Okay, plan a presentation shortly. We're going to define this and do their tectonic settings. We're going to show some modern examples which are very poor, but what we have in the modern world. They're much better in the ancient. What are the evidences of SABSEL basins in the sedimentary column? And I'll show 4 examples of ancient SABSEL basins, all of which are significant to oil and gas exploration, and notably the Gulf of Mexico Norphlet terrain. Conclusions and how to use this model. Subaerial basins below sea level. Okay, they're formed in 2 times. They're in the Wilson cycle at the beginning of rifting in continents when the big plates are ripping apart. We have these small Atlantic basins of that type, and that's the extensional basins. And then at the end of the plate tectonic cycle, when the continents are coming together again to form the big plates, we have collisional basins, and they are terminal basins of J. Tuzo Wilson. And both of them are involved with salt, and salt is the key. If you see salt, it's very prospective. Where do we have these presently? Well, the Dead Sea is the deepest example at 1371 feet. And we have one, I'm going to show the Lake of Sal in Djibouti. And if you wonder about ours, we have one in Death Valley, which is 282 feet below sea level. It's going to be a long time before the sea gets back in there. Okay, and here is a space picture of the Djibouti example in the around the Horn of Africa. I'm feeling for my pointer. Okay. And the basin is somewhat below sea level, 410 feet in one place and 300 in another. And it illustrates, okay, this is the basin here. And it's pulling apart, and there are all sorts of volcanics in here. The next slide shows this. Geology slide. This is important because this is what you get at the beginning of these basins as the plates spread apart. And here we have the Danakil Horst prevents the sea from coming into this low area. And in this area we have Pliocene volcanics. We have recent volcanics in the red, which are basaltic volcanics, giving off a lot of CO2. So that's a hazard if you were exploring in this area. You might get a well that produces CO2 instead of oil. You also have the Miocene series, of which you have in the sediments, you have lacustrine lakes and the good source rocks. Salt is being mined in this area, and people are terribly hot. They go in and they mine the salt and carry it out. What is the evidence of deposition in a subaerial basin below sea level? Well, for one thing, we have deep water deposits over subaerial deposits with no transition. This is very important, no transition. Cross-bedded sand dunes under the marine sediments with no loss of dune form. No loss. The dunes are still there, and they are not reworked. You get thick reservoirs with porosity preserved to great depths. And then you have salt deposits, and sometimes the salt deposits are above the shredding center, and so this is the beginning of one of these great big super basins because you get 2 levels of production, one under the salt and one above. And so one of the evidences that the place dried up is you have canyons along the side of the basin which are graded to the bottom of the basin. So when the water dried up and the salt was deposited, the canyons, the water in the canyons had to get down there and cut down to the base level. Terrestrial deposits sometimes are over the salt or marine sediments with no transition. Sand facies then are displaced far into the basin now. Deep karst and marginal carbonates, and you'll watch for this in some of these examples. So let's move to the examples. The former subaerial basins below sea level are the southern North Sea, the Mediterranean, South Atlantic, and Gulf of Mexico. And they're all very prospective. Now the southern North Sea is a collisional basin. And the reason that's important is in collisional basins, you have the collision and you have the pre-existing rocks. You don't have the opening of a set of rocks that have to do with the extension and the formation of the earlier basin. You have what was there when the basin began to subside below sea level. And here is the southern North Sea, the Permian Basin. Now above that you've got Permian and then Triassic and Cretaceous. So you've got a whole strat section, but what we're interested in is just the southern. And there's the North Sea. And all of those red things are gas fields, and the shape generally is because they're in sand dunes. And so the grain is like this. Now there's a lot of structure involved too. And what is this related? Now in here, this is Groningen. That was the first discovery, and it was about 95 trillion cubic feet of gas. And all of these other things added together in 1990 were assumed or calculated to be about 150 total reserves. And so once again, the biggest field by far was the most reserves. However, keep this in mind for later when we talk about these basins. Think of that pattern. And here is the situation. You had a basin which was about 250 meters below sea level, and in the north you had a barrier and a lake along the edge, and all through here you had these sand dunes. And the sand dunes are hard to predict where they're going to be. You want to find them with wells or seismic because the wind carries the sand where it will. And it's very hard to say the sand came in here and it's not going to be over there, because if the wind blows it over there, it'll pile it up over there. Whoops, now what? Okay, thank you. All right, back again. Right there is this cross-section we're about to look at. And I've drilled these things in Louanne Field. They're fascinating. Here's your dunes, and they're all cross-bedded, and they go right up to the unconformity. Sometimes a little white sand right in here. Water did influence it a bit. But what happens is, when the barrier breaks, the water comes in at the barrier, but it doesn't agitate here, it just agitates the barrier. And those of us who have had tubs, so many people now take just showers, but you sit in a tub and have the water turned on, and the water rises up past your knees. Well, that's what happened here. It just flooded in and rose up, and it may have been feet per day, but it didn't destroy the dunes. This is not the typical transgression you think of in a transgressive systems tract. This is all of a sudden. And at the top, when the water is coming in, you have this, first you have this quiet deposition in which the shale deposits. And this is the Kupferschiefer, copper shale in German. It's a metal-rich shale, and it drapes upon the dunes just like snow falling. And it covers the dunes not by transgression, but just in drapes upon them. Underneath we have the Sebga and the desert floor. And I've driven across a desert floor in the Sahara. And you can go for miles on a very smooth place with just the rocks left by the wind carrying the sand away. And then you come to a sand dune field. But so when you're drilling, you can get between these, and it can be discouraging because all you get is tight sheet sands and fluvial. Now, here in this area, they were fortunate in that the pre-existing terrain was a tilted set of carboniferous, and the carboniferous was giving off natural gas. And so the gas moved up into the dunes. The Mediterranean Sea is another example, and this one is a collisional basin, just like the southern North Sea. So the stuff underneath is what was inherited from an earlier time. And the basin got barred, and you had, it was a former Tethys Sea, and you had a marine shelf with deep water, but then you suddenly got saprophyll, which is a very stinking black mud, a good source of oil if you had enough of it, and also it can be a source of gas, and it's biogenic gas. This is just a marsh. And in the area you get the river channels cutting down to the basin floor, and you get deep karst. And deep basins down to 12,000 feet below sea level. Controversial. There's a big argument still going on by various sections of geology, and each one has the answer. Some say it dried out entirely, and some say it only went down 3,000 feet, and they'll beat you around the head and shoulders with their evidence. Maybe both are right. So here we are, and here these are salt basins, and we know these are salts because people have drilled through them. They've dropped cores into them. In here we have a number of examples. We'll show this in a minute. That's a core right down in the bottom of the ocean. Here we have the new discoveries of natural gas. And I missed this. It's so simple when you think about it, but there were no source rocks in this area, and we knew that. And so Amoco, we did not recommend Amoco to get involved, and you could see big structures. Well, what we didn't figure is that saprophyll is nice and cool, and it was making marsh gas. And this marsh gas got in the oil, and it filled these reservoirs. And the beauty was that nobody understood about this gas until one comment by a vice president of a company drilling in the area was asked about what is the carbon isotopes of this gas, and they said, oh, very negative. It's all biogenic. And all of a sudden, there's source rock all over this place, because right before the salt, there's saprophyll, both in Spain, opposite this area, and over here. What a surprise! Right at 100 trillion cubic feet have been found in Zor and Leviathan. What a wonderful name. Okay, this is that little core place I was showing you. And here, when they did the deep sea drilling core, they found the shallow water sediments with abundant pyrite, and this is a saprophyll in here. And here is the unconformity, and right on top of it are deep water oozes. And so this is an instant in geology. This is almost like meteors. This is the ultimate system, the down warp system tract. The ocean left entirely all of a sudden. Now, that's controversial. Here is this is Sicily, and here is the Chilean Plateau, which is a big limestone plateau. The Medina Escarpment, you drop off of that, and people have drilled wells in this area, and they had very little circulation. They couldn't keep water in the hole, and we'll see why in a moment. Here's the interpretation, if indeed this is all dried up. Now, there are some people say it only dried up to here, but in this case, the point is they come down here, and as the air descends, you wonder how it got so dry and formed the salt. This is adiabatic heating. You compress the air as it falls. So you start with a Ghibli up here at 100 degrees Fahrenheit, and I've stood up there in those, up to 115, and comes over here, and as it goes down, it goes through the lapse rate of 9.8 centimeters C per 1,000 feet. By the time it gets down to the bottom, you're 169 degrees Fahrenheit. So, and I loved the German who came to me and said, oh, now I understand. How can you get these potassium salts with a climate that is not hot enough? Well, you get in a hole like this, you got enough heat. Here's what the point is about those limestones. When the sea goes down, the streams go into the limestones and they work their way down to the lowest level. Huge caverns in Yugoslavia. Don Russ took this picture. And this is the case in Spain, where they explore very deep caves, and cavers have worked for for records on how deep I can get in the earth. So these are an explanation of why, for instance, Zoar, which is a limestone just capped by the Messinian salt, is listed as having extremely good porosity and permeability. Well, you can imagine. So it stuck up and the rain water fell upon it and it dissolved partly. Okay, now then the question of these gullies, these ravines leading to the bottom of the Mediterranean. I was in Libya and we had trouble with our seismic. We had a thing that looked like a snake and we couldn't figure out what that represented. It turned out it was a channel like this, cut in Libya, going to the Gulf of Mexico, going to the Mediterranean, full of sand, full of fresh water too, but shh, don't tell anyone. We don't want to be forced to complete it. And now, here we are at 1.5 seconds. This canyon in offshore Nile has cut way down. That's one of the evidences. Now, another problem is that, of course, everyone's interested in let's prove one's theory or the other. Here's a gentleman who worked on the depth of water in the underlying sediments. And he found that the depth of the water was, by paleo, is water depth, planktonic foraminifera, or no, benthic foraminifera. He said it ran from 3.8 kilometers up to 3.6 kilometers at the base of the salt. Well, he's right. I mean, I don't argue that data. This is a pre-existing terrain. So it doesn't matter that it's old and deep. The water left. And so right here is that core again. And that saprophyll's right there. It hardly shows up and it's not got any fossils in it because it's acidic swamp deposit. So yes, he's right here, but his conclusion, I don't think so. And he took the cores, information from the wells far to the east. No, is that west? Yeah, the President Basin. And what does that say? Oh, darn. East, central, and west, central, and east. So that's east. But the point is, right underneath the salt in each case, you've got the saprophyll. And so it doesn't matter that he's got very nice timing and all in this. It has nothing to do with the fact that the Mediterranean dried up. The South Atlantic, I'm not going to do a great deal in this. It's a fascinating place. You've got two levels. You've got a level of billion barrels of oil in the sands above the salt, and go through a thick salt, and underneath you've got just as good, if not better. Tilted fault block structure is bounded by normal faults. That's common in the extension terrain. You've got basalt volcanics. You've got a couple wells out there which are pure CO2. Very disappointing, of course, when you try to test the gas and, take it through the burner and it won't burn.
Puts out the pilot.
I'm sorry?
Puts out the pilot.
Oh yeah, it can definitely put out your flare. The lacustrine organic rich shales, bacterial and coquina, I'm not sure about the spelling, carbonates are reservoirs and are oil productive, and they're sort of fresh water or mixed environment. No one's really sure of what these thrombolites are, but there's a good field trip in Salt Lake City where they're going to the thrombolites, the bacterial carbonates in the north of Great Salt Lake. It's a fairly heavy walking and all, so it's not for the armchair scientists. And here is a map showing the amazing extent of this. And the next example is going to be off of Brazil, right in there. And that is, here's a seismic line just for fun. This is Tupi Field. No. Lula. Billions of barrels of oil down under the salt in this uplift here. And there are some questions about what is the distribution of CO2. Seems to have to do with the faults as far as I'm concerned, but anyway, it's always a risk. And wonderful structure and a huge amount of traps of all sorts under the salt. Now, this is where it's really important. This is the Norphlet. This is ours, Gulf of Mexico. And this is a real discovery by the U of H consortium in the Caribbean and Gulf of Mexico. What they found was now they're able to see some magnetic stripes in here indicating the direction of the movement of the Yucatan. And here's the data, and the original salt, which was once together, has been split. There's an area in here of supposedly of no salt. And the salt is in here, and obvious on the seismic. They've got some domes in here, and they've got domes, of course, here. That's the 6B escarpment. And in the Gulf of Mexico, the Norphlet is a desert dune sand located on top of the Louanne. And this is an extensional basin. In fact, there is just a hint of there may be a terrain under the Louanne out in this area. But of course, these Norphlet wells are already 20,000 feet deep. And you have to drill through the salt weld or the salt that's left from the original Louanne and into the underlying rocks to see if you can find the reservoirs like the South Atlantic. What would be the clue? What would you look for? Well, what you look for is there any waxy oil in any of these rocks in this area? Because that is from lacustrine beds, and that would indicate there may be some source rock underneath the salt. But that's a separate topic entirely. Here, we're looking at the dunes themselves. And where do we have this? We have a type locality of the sand dunes of the Norphlet here in Marianne Field, Mobile Bay. We've got the new shell and now total discoveries out here. Big fields. And we have some reports that there's a Norphlet in here. I'll discuss that. This is Balam, which is a Mexican field. It's producing oil from dunes, dune sands, different names, but dune sands. And in Atascosa County, there's a well that went down and through the subgut. And they said, the article said, oh, they've discouraged, they didn't find any sand dunes. Well, all right, so they found the desert floor. How close are those sand dunes? You know, and you don't drill to 20,000 feet on chance, so.
Which well was that one?
I don't remember the name of
Was
it.
it one of the Panhandle?
It's a Atlantic well. It's very early, but very deep. And it's published in the GCAGS. Just an obscure little.
What county again?
Atascosa. And here's Marianne. And this is the fun part. They drilled into a dune field, which is shown on seismic here, where they could see the thick dunes in this area. And they got into Marianne Field here, which is partly structural. And they've got hundreds of feet of Norphlet Aeolian sandstones, one after the other, just pure sandstone, 7 to 15% porosity, and low permeability, but they got a lot of it, and it's all full of gas condensate. The good news, the bad news is it's got a significant portion of H2S. And so they had to be very careful since this is right opposite in Mobile Bay. There's a big city nearby, so you don't want to blow out a H2S well. But they finally got permission to do it. And here's the top of the porous Norphlet, and they've got a little bit of Norphlet up here. Now, I've seen a core of the Norphlet. It's a cross-bedded red sandstone. Well, in a core, it's not very cross-bedded because you only got that much, but it's definitely tilting, various tilting beds in the core. And at the top of the core, it's full of pyrite. And that was an opportunity where one could see they started coring too early and they got some of the overlying material. And that was the brown dents of the Smackover. Very finely laminated. organic rich, full of pyrite, and when they drilled through it, it's overpressured. The point is that it generated the oil and gas that went down into the Norphlet. Now the Norphlet is 450, here it is. Oh, they didn't say, well, it's 415 degrees Fahrenheit. And so the oil was pretty well turned into gas. So Marianne is a gas field. And this is the same situation that we discussed earlier. The ocean came back in, and these dunes have kept their dune shape. And therefore, you can see them on seismic. Here is the big picture, and all of these dunes are due to a wind from this direction because they're longitudinal dunes. Here's the situation. When they were deposited, they were dunes sitting on the Louanne Salt, but they're heavy, they're 600 feet high. They pushed down into the salt, and so they made these things like this. And that's from the Norphlet Field, and these are all from Mankiewicz AAPG and also Weldon Frost of Mobile, who did a whole talk on this, and if you can find his talk, it's got a lot of extra detail. Now, if the situation that we have there is that the brown dense drapes over these dunes, covers them over, it's a good seal. It used to be the source pushing the gas down. Now the gas is out, it's a seal. If it was a transgressive system track, it would have had been, the dunes would have been cut off at the tops as the sea crept in. The sea did not creep in, it flooded up. And therefore we have this situation. Seismic, and this is most startling. The dunes set down into the underlying salt. When you get to salt layer level, you see these little eyes. In German, it would be Augens. You see them in blibs and igneous rocks. But these little eyes are there. And you see them in a bigger scale here. Now, the reason that's so fascinating to me is that when ION had their big lines in the walls of the SEPM, I noticed these little tiny eyes looking out at me at the level of what I thought was the Louanne. Unfortunately, ION had only salespeople and didn't have any geologists there to discuss this. But they say that at Salt Lake they're going to put this up again. So you might want to look for that, because it is possible that these dunes are much more common than we had given them credit for. The Gulf of Mexico could look like that map of the Permian Basin with all those gas fields. And these aren't gas, the fields are big in the Norphlet. Okay. Sand dunes and bloody deposits and gravel plains of the desert are immediately overlaid by quiet marine water deposition without transition. So suddenly the water comes back. That's a subside basin. They retain their topography. There are salt deposits. And how would you get a salt deposit if you didn't have marine water coming in, drying up, and maybe it comes in waves, because the amount of salt you get from 1,000 feet of water is not anything like the thickness of these salts. So you got to keep bringing it in. And the salt deposits, especially the potash ones, are signs of extreme aridity. And anhydrites are indicative of a SEBCA environment, which may overlie deeper water sediments with limited transition. So you can have a basin which has nothing in it in the extension. And so you've got this terrain down below sea level with all sorts of interesting things, volcanics and lacustrine rocks, reservoirs. But you can also have the opposite case, where you don't have any of that underneath. It's just luck of what's underneath. If the basin collapses and the water can't come in for one reason or another, you've got enough marine water coming in to deposit salt. And right above that, you could have this basin again, like our Norphlet. in the Norphlet, the basin was, we don't know how deep, but somewhere in the Norphlet, there should be a bathtub ring of black smackover. That first set of beds, which are just source rocks and black and tight and finely laminated, should have butt up against the edge of the basin when the fresh water, the more marine water came in. I've talked to a smackover expert, and he says there's no such thing as deep water smackover. And that's because he studied the shelf. But when you get down here, different case. Okay, and on the basin margins, sediments, filled canyons, and deep karst and carbonates give evidence of former low water levels. And that may be why Zor is such a great field, because they report that the Miocene carbonates are very porous, and even the Cretaceous carbonates are porous. And that would be quite understandable if it stood up in this basin which the seawater had left, and what rain occurred went down through it, creating these caves. So, a subaerial unconformity does not necessarily mean uplift. Remember in your stratigraphy classes, the professor said, and then the land went up, and then it went down, and then it went up again. Well, it doesn't have to do that. To get this deep water over the shallow sediments, deep sediments over shallow sediments, you simply fill a pre-existing hole. Reservoir porosity of the sandstones can be good, and drowning of the basin by seawater can be rapid. Can you imagine waking up, you're camping on the sand dune, you look over there, and the water has risen at night so that now you're on a sand dune in a sea, and then 2 weeks later you're swimming. Only at the entrance of the basin are channels cut. So what are we doing? The academics are studying the mouth of the Mediterranean. They're looking for how that water got in through the Gibraltar, because once you dissolve, and this is the final statement, once you create this big hole, you've got to have a really big area to let the water come in, or it will go down and evaporate again, and you won't fill it up. So they've been looking, and they find some evidences of channels around the Straits of Gibraltar, so that when the sea level came up enough, it flooded in from several entrances. So this is a very economic idea, because if indeed we have the Norphlet in the bottom of the Gulf of Mexico, and these fields really are hundreds of millions of barrels, and what if it looks like the southern North Sea with all of that production? There it was gas and small, and here, well, 150 GCF total, but here it could be billions of barrels. Thank you. And I take questions or comments.
Questions? Walter?
Do you recall what the H2S is